around here, the main outcome of this is what? This was in the saturation region, right? This was the current equation in the saturation region. The main outcome of this, or the physical understanding that out of this, is the value of ID is not dependent on VDS anymore. VDS was in the previous equations. In the quadratic, VDS was there. In the previous equations for current, VDS was there. Now, VDS is not there. VGS is there, right? So we have what? We have a current that is going to be flowing through this device based on the value of gate voltage that I supply, right? So I've created a voltage-controlled current source. Independent of the value of VDS, I will still be pushing ID through this device in saturation, only in saturation, right? So that's a nice thing, because now if you think of amplifier operation, what do you want to do with amplifiers? You want to be able to measure a phenomena and then amplify the output based on the measured phenomena. So if I'm measuring something from VGS on the VGS terminal, I will produce an amplified version of that in the drain current, right? And then, fine, this is a constant current, so let's say I want to convert that to a voltage, I put a resistor, because it's a constant current. It's a current source with a parallel infinite output resistance, right? If I put a resistor in series with that, then I will get a fixed voltage at the output, which is nice. It's like a voltage source with zero series resistance, right? So that's the beauty. That's why you can operate op-amps, these devices, in saturation mode as amplifiers, right? Because we've created a controlled current source. Controlled by what? By the gate voltage here. So this is an example I will not go through. It's very, very simple. Just goes through some of the parameters and the dimensions and stuff that we discussed. But we will go through another example later, and more relevant. Yeah. So everything we've discussed is on the N-type MOSFET, yeah, or the NMOS device, yeah. The P-type, or the P-type device, or the PMOS, it's called. So it's called the PMOS, or it's called the P-type device, or it's called a P-channel device, or it's called a P-channel FET, or whatever you want to call it. There are many names for it. It's exactly the same if you put absolute value around the voltages, because the voltages are all flipped, right? So let's look at the construction and then quickly run through, but we won't spend too much time on this. So here it's exactly everything is the opposite. So I have a N-channel substrate versus there I had a P-channel substrate, and then I've put P-type materials. What do you think I will be doing? I will be applying a gate to source voltage, but this gate to source voltage will be negative with respect to ground. This will still be connected to the body. This will still be connected to ground. Initially, we can connect this to ground as well and talk about if we do this. If I connect this to ground initially, what's going to happen? If I connect this to ground initially and I supply a negative gate voltage. Negative gate voltage means electric field is in this direction, right? If electric field is in this direction, what happens to the positive charges? They go up. What happens to the negative charges? They go down, right? And all the N-type, free electrons in the N-type material will go down. I create a depletion layer. Initially, I will create this depletion layer free of electrons. I keep adding more electric field due to a negative voltage. I will create a channel. This channel will be what? What type of material? I'm pulling all the holes to the top. So it will be P-type material. So it's a P channel, right? Because I've added a negative voltage. Okay, so, and here, same thing. I will add, so this is VDS equals to 0. Then I will start adding a VDS voltage that is negative here with respect to ground, or negative with respect to the source, which means what? The electric field is in which direction? This direction. The electric field due to this source is in this direction, right? So now what's going to happen? The holes will move from this side to this side, and the holes are carrying the charge. So where is the current direction of current flow? From the source to the drain. Before, the current was moving from drain to source. Now it's from the source to the drain. Right? So everything, everything we said applies, except that you will see the equations. All the equations are the same. They will just put absolute values around the voltages so that we can draw the characteristics here. Okay, and that same idea, same philosophy behind, you have a source at a certain level. Before, for the N channel, we had a gate voltage that was higher than VT, that was equal to VT plus VOV, right? This was the gate voltage, VGS, was equal to VOV minus VT, right? Or VT plus VGS is equal to VOV, right? So that the difference between the overdrive voltage, is equal to what? The VGS minus VT, right? That's what the overdrive voltage. This is one. The overdrive voltage is equal to the gate to source voltage minus the threshold voltage, right? It's the same here, right? For the N-channel device, we had source at the lowest level. We had a gate, and then we had a drain. The drain voltage was, anywhere starting from 0, close to the source, and that will give me the start of the beginning of the triode region characteristic. And then this can move up. This is the drain voltage. The drain voltage can be, let's say, up here. If the drain voltage is up here, I'm operating in saturation mode, right? So that was the NMOS. PMOS is exactly the same, but here's my source. The gate is a little more negative, and the drain can be, starting from 0 all the way to much more negative. Triode region, saturation region. So exactly the same, except that the voltages are negative. They're all negative, and the direction of current flow is flipped. So that's what I will have to say about the PMOS. Okay? Yes. So here they talk about this absolute value, so that everything else looks the same. We will use absolute values for voltage, and we'll see the equations for current now shortly. Okay. One interesting thing that you will hear quite a bit, you will hear the term a lot. You will hear the term complementary MOS a lot, and complementary MOS is what it's CMOS. And CMOS, this is a word that you will keep hearing. CMOS is the workhorse of the electronics industry. Until today, it's the workhorse of the electronics industry. Oh, I don't know since when. No, I don't know when. Since when I cannot. Yeah, they're saying by 2009, the CMOS technology had taken over many applications. But just a few years later, possible with bipolar devices. Yeah, so starting 2009, I would say it became the workhorse of the industry. And what is CMOS? CMOS technology means I have PMOS devices and NMOS devices on the same chip. That's all it means. Yeah. Right? Why is that interesting? Because again, here we studied the NMOS device by itself. We looked at the PMOS device by itself, right? But remember the diode circuits that you took in the last chapter. Just combining some diodes with Zeners, you were able to do some fancy stuff, right? Can you imagine now being able to combine NMOS devices with PMOS devices? Again, we will not be able to expose you to all the fancy stuff you can do in this course. We'll give you some exposure, but there's a lot of fancy stuff you can do with combining PMOS devices and NMOS devices. People came up with very fancy ways to develop circuits that do different things, like mirroring current, for example, in two places in the device. You make them exactly equal somehow by using PMOS devices on one side, NMOS devices on one side, for example. Right? So sometimes you want to do that. Sometimes you would like to do stuff like that. So there are applications that, again, they're part of a maybe more advanced course in in electronics. But again, here we introduce you to PMOS and NMOS. You know what the structures are like. This is how they function. CMOS is a semiconductor wafer that has both technologies on it. Yeah. When it was invented, I don't know. You checked it up? 1963? I don't know. I mean, maybe. Yeah. Maybe the BJT was invented in 1963, but we'll look at that in the next chapter. Yeah. We will not discuss the operating of the MOS transistor in the sub-threshold region, meaning operation with VG less than VT. You know, if you're applying a gate voltage less than the threshold voltage, we assume that this is when the depletion region starts to form, right? And then beyond that is when you start to create the channel. So really, what happens in more detail beyond VGS is equal to VT, we will not discuss. That's discussed a lot more in chapter 13. We will just skip that. I mean, they don't have a big section about it. This is a cross-sectional view of, an example where you put an NMOS and a PMOS on the same silicon wafer. And again, the devices have the same, source, gate, and drain terminals, same as the individual devices that we talked about, right? And so here's the silicon oxide insulator placed between them. And again, because you're using a P-type substrate, you create an N-type well, so it's like a substrate for the PMOS device, right? So again, this, as we said, this is the workhorse of the industry today, and I mean, we can see now where, remember the construction video that I showed at the first class, right? See, this is where it's all coming from, right? And then you can imagine, because you have to create circuits with this stuff. So you actually build bridges between all of these. Right? If you have a circuit with 2 MOSFETs or 2 diodes or whatever on a substrate, you actually have to connect all of this stuff. That's even more of the building block stuff that we saw before. And people working on VLSI, VLSI design. So we have a big team at Texas A&M in College Station whose research is only on VLSI. So they only do VLSI research. It's a huge team, and they sit and they build this stuff. So they sit and they build and they look at the real estate on the chip that you have available and the sizes of these channels. They get into all of that from a research perspective. Okay, voltage and current characteristics. We talked about the characteristics of the voltage and current across the device, but okay, before we move on, let's agree on a symbol. Because we have to build a circuit with this, so we cannot be putting N-type, P-type, N-type, and drawing these wells. So what the circuit designers did was, okay, we agreed any of these can represent the NMOS device, right? So, or the MOSFET device. I like to do this. I like to use this one, the simplest one, and it tells you if this is an NMOS device, the direction of the arrow is where the current is flowing from the drain to the source. Right? I like to use this symbol. It's the easiest. These symbols will be more relevant when if we talk about the body diode. I mean, it's just quickly, okay. I will just quickly touch upon it because I don't want to spend too much time on it. So remember, this is what for the NMOS. This is a P-type device. This is like a diode, and this is like another diode, right? So they are both reverse biased. If I put a positive voltage here versus ground, a positive voltage here and a positive voltage on this side, right? And we want that to happen. We want, when the device is open circuited, to have these diodes in reverse condition, reverse bias condition. But we also said that the source is connected to the body in the NMOS device, correct? So in normal conditions, current is flowing from drain to source, right, in the NMOS device. But what if your circuit somehow is forcing by, your circuit's creating a current source? Like, remember, this MOSFET was in amplifier mode, it looked like a current source, right? Let's say your circuit, your external circuit, has a current source that is forcing current in this direction. Is current going to flow or not? If your circuit is forcing it, you have a MOSFET device, NMOS device, that has connected to an external circuit that is forcing current. Let's say I'll draw it here. Your circuit is forcing current in this direction, right? Normally we said normally that this is the direction of current flow from drain to source in an NMOS device, right? That's what we said. And based on all the values of voltages that we talked about, the current will flow from the drain to the source, right? However, because my source is connected to the body, right? If I try to push current through the source, I have this device and it's out there, I just try to push current to the source. what's going to happen? Pushing current through the source is like pushing current through the short circuit, right? Will forward bias this diode, and current will flow out of the drain, right? And that's the body diode. It's a parasitic diode due to the construction of the MOSFET. We don't care too much about it when we talk about amplifier operation or small signal analysis because it's not a big deal. But if you talk about power electronic applications or switch type applications, in switch type applications, if you have any inductances, what does an inductance do? Inductances create a phase shift between the current and the voltage, right? Is the current lagging or leading the voltage? Exactly, current lags the voltage in an inductive type application here. So if my voltage becomes negative, if I have a resistive load, this is the voltage and this would be the current, right? If I have an inductive load, this would be the voltage and the current may look like this, right? So what we see here is that, 90 degrees, no, not, yeah, if it's a pure inductor, yes, it's a 90 degree out of phase. But here, basically, let's say in this case, I have voltage with a certain polarity and current with a different polarity, right? So remember, we had voltage, if voltage is a certain polarity, current should flow in this direction from positive to negative. But if I have an inductive load, sometimes in certain cases, I will have a positive voltage, but the current will be forced to flow in the opposite direction. Why? Because I've stored energy in my inductor. Why is it doing that? Because I've stored energy in my inductor. This energy has to go somewhere, right? You're trying to put an opposite voltage across the inductor. So the inductor has a certain voltage across it, right? A certain negative voltage, for example. It stored energy, right? What happens? You're now trying to flip the voltage across the inductor. When you flip the voltage across the inductor, V is equal to LdI by dt, right? Inductor current takes time to change, right? If you try to flip the voltage across the inductor, if this is a negative voltage, you're trying to make this change negative. This slope will try to be will decrease. It was increasing initially when the voltage was positive, and now it's decreasing. So the current is trying to go down to zero, but it takes time for that. So there will be a point when the voltage and current will not be the same polarity. So there will be circuits in power electronics, for example, that will cause this, that will trigger this to happen. And that's called, freewheeling current. It's freewheeling current. It's current that is in the circuit that is because you have an inductive type circuit there. So, and that's one of the important things if you want to, the effect of the body diode stuff is important when we discuss something like that. Okay, so that's this body diode here that we discussed. Okay, so I wanted to touch upon that. After touching upon that, let's continue. So any questions on that? I mean, do you agree that current can flow in the reverse direction in certain applications? In applications that we talk about here with amplifiers, nothing, no problem at all. No issues. But in certain applications you have to consider that, and it's a parasitic diode. It's called the parasitic body diode. It exists because of the structure. Does not happen in the BJT device. Does not happen in the BJT. One of the advantages of the BJT device in that application. And we will talk about how we.
What diode does not have?
This body diode issue.
Body diode.
The body diode, yes, this parasitic diode is because of the construction of the device, right?
So it does not have a body diode issue?
In the BJT, no, because the construction is different. Yeah. We will talk about BJT next week. Yeah. So this will be the symbol that we will use. I just wanted to touch upon this reverse current because I said this, the polarity of the current is always in a certain way. In this model, yes, it is for our applications. But you just have to know that there is something called this body diode. It will come up later, maybe not now, not in this course. Okay, so that being said, the symbol, this will be the symbol that we use in the circuits that we will develop. We talked about the characteristics, so we will draw them here. So this is the summary of what we've been talking about for the past 2-3 classes. So this is the summary. The summary is fine. You have a diode now with a MOSFET with a symbol that we like to use, and then we have VGS, a gate voltage, and a certain drain to source voltage, and then the drain current. And the characteristic is what we've discussed. Initially, sort of looks like linear, but then we said that what? ID is a drain current. No, not diffusion current. Yeah, it's a drain current. Yeah. So we said that this follows the quadratic form, and this is called the triode mode of operation. This is called saturation mode of operation. In saturation mode of operation, I have a current here that is independent of VDS, right? It's independent of VDS. In the triode region, we will see here. Look at the equation. So these are the equations in the triode region. Triode region, equation, saturation region. Remember, saturation region and triode region are you can define them by the value of VDS, right? If VDS is less than the overdrive voltage, we're in triode. If VDS is greater than the overdrive voltage, we're in saturation, right? So, and hence, if you look at this current, these two are the same. That here it's dependent on the gate voltage, but it's also dependent on the drain to source voltage quadratically. So changes in VDS will change the current, which is why we have this quadratic form, right? And then here they just remove VGS minus V threshold, and they replace that with the overdrive voltage, VOV. It's the same, right? In the saturation region, I do not have dependence on VDS, right? Which becomes a nice characteristic for operating as an amplifier. So triode region, saturation region, and then cutoff is here. Cutoff means there's no current flowing in the device. Cutoff is, ID equals to 0. So regardless of the drain to source voltage that you have, ID is equal to 0. Because gate voltage is less than threshold. Remember, if the gate voltage is less than threshold, I'm not forming a channel, right? So the device is cut off. Okay? So now, if I'm operating as an amplifier, we said I like to operate in saturation. How about if I'm operating as a switch? Just a switch. I want to operate as a switch. Switch operation is in two different applications, two main applications. Digital circuits, you want ones and zeros. That's switch type operation. Power electronics, you also want to turn on and off, like the rectifier stuff we discussed last time. You want the diode to be on, you want the diode to be off. In power diode, it will be on and off based on external circuit conditions. MOSFETs, you can be on and off based on my gate voltage. I command you to be on and off. So if I want the half-wave rectifier, instead of to see the full half-wave at the output, I just want to see part of it. I cannot use a diode anymore. I have to use a control device. Right? This control device will allow the current to flow through for 1/4 of the cycle, 1/5 of the cycle, depending on what? Depending on your gate voltage. It will operate as a switch. When you operate as a switch, you want to do what? You either want to operate in open circuit, theoretically speaking, which is what? Cut off, right? Or you want to operate in short circuit, but again, there's current flowing in a channel, right? This channel has a resistance. Right, so where do you think we want to operate? Where the channel has the lowest value of resistance as a switch. Where does the channel have the lowest value of resistance? Here, in the linear region, triode region. So in power electronics or in digital circuits, this is where we operate. We change the gate voltage and we operate here. Change the gate voltage, we operate here. Change the gate voltage, we operate here. We don't want to operate here because we want to operate where the slope exists, so that the resistance, which is here, the slope is 1 over the resistance. Right? If the slope is 0, the resistance is infinite. If the slope has a reasonable value, then this resistance is small. Right? So in power electronics or in digital circuits, I operate here and here. Right, either on this straight line or cutoff mode. In amplifier, I operate in saturation mode. We see the difference? Why? Okay. So this, again, is a summary of everything we discussed so far. Everybody's okay with this? Good. And this is the, again, the summary we also discussed, okay, the various values of voltage. So typically we always keep the source at the lowest voltage. And depending on where the gate and drain voltages we have, it will define what if we are in the saturation or in triode region. We said that VDS greater than or equal to overdrive voltage is saturation. Right? So here's my S. This is my voltage at my source. This is my threshold voltage. It's a device characteristic. I've placed my gate voltage here. This gate voltage is higher than the threshold. The amount it's higher than the threshold with is called my overdrive voltage. Right? So this is my overdrive voltage. I take this, for example, and I put it here. This will be my overdrive voltage. Now, if I'm operating with the drain voltage equal to or more than the overdrive voltage, I'm in saturation mode. If I'm operating below, I'm in triode mode. Okay? And then the PMOS is exactly the same, but everything is negative. Everything is negative, but exactly the same. We see now the summary of everything we talked about? Okay, good. So now we will, so they redraw the characteristics here for different values of, gate voltage. We said that, we drew one, fine, but now we change the gate voltage. We change the gate voltage. We change the gate voltage. Make the gate voltage 0 or less than threshold, and this is now the characteristic that you will see in a typical datasheet. I did not bring a datasheet, sorry, but if you take any datasheet, you will see this.
And it changes every time you change. There will be a new curve.
Yes, every time you change the overdrive voltage, which is controlled by the gate voltage, then you're on one of these new curves, on a different curve. Okay, so which means what? That if I want to control the current, I'm saying I'm creating a voltage controlled current source on my output. This is my output. It is a voltage controlled current source. This is my drain. This will be my source. This is my output stage. My output stage, this is ID, is equal to that equation that we have here. So this is this equation. Only in saturation, right? Only in saturation can I use these equations. Triode, I have to use the quadratic, okay? But we are not going to operate here for amplifier. We're only going to operate in saturation mode for amplifier, so you can use these equations. Right? So it looks like what? The current ID is equal to half KNW over L VOV squared. VOV, which of VOV? One of them, depending on the gate voltage. These are all device characteristics from the size, the width, the length, the height, the capacitance. All that is device, and then your only control variable is the overdrive voltage, which is the gate voltage.
And all of this is ID.
Yeah, this is all ID. This is ID1, ID2, ID3, ID4. All of these are. Yeah, this is the drain current. So you've created a current source.
Even the positive, we look at the drain current.
What do you mean positive?
And the PMOS.
Yes.
It's all the same.
It's all the same. Yeah, the same. We will have a summary of the PMOS next.
I think it's the opposite. We would look at VD.
No, we will look at the drain current as well, but it will flow from source to drain instead of from drain to source.
Okay.
That's the only difference.
So instead of being VS,
the PMOS, we will come because we talked about it before you came, but we will.
It will be VSD, it will be VDS.
Excuse me.
VDS.
It will be VSD. Yes, fine. Sure.
It should be.
Yes, but you can put VDS in absolute value. So I think they will keep.
VDS
No, because VSD is equal to negative of VDS, right? They're just, if you use that notation, VAB is VA minus VB, then VBA is just the opposite of it, right? So if you just use one of them and put the absolute value, khalas, you're done.
So VDS is equal to absolute value. No, absolute value of VDS is equal to VSD.
No, absolute value of VSD is equal to VDS, right? If you want to call it that. But anyway, we'll summarize this PMOS again, the way we did for the NMOS. So do we see now, this is my output. What's my input? My input is VGS. This is the common source, right? And this is my gate input. So this is my model. I just have a gate, a source, and a drain. This is because, and this is my model for this situation. Remember, what did we say now about what happens in the saturation mode as VDS increased in reality. We said in reality, in this case now, the slope here is 0, so slope is 1 over the resistance, and now because it's 0, it means the resistance is infinite. So I kept an infinite resistance here. How about in reality? Practically, what happens really? Practically, what's happening? We said that, practically, what's really happening is that this current is actually increasing a little bit, right? So there is a slope. There is a slope to that. If there's a slope, the resistance is no longer infinite. It has some value, R output. We will calculate that next. But we saw that, right? We saw that this is because of what? Channel modulation, channel length modulation. We will talk about that shortly. Okay. So everybody's okay with this now? You're comfortable with this characteristic? See what's happening? Okay. Okay. These are just the equations, the equations that we discussed before, and then we'll talk about the model later. I mean, say they just drew the ID versus VGS. They just took the equation and plotted it for different values of VGS and ID. This is, again, we said that the model of the model will look like what? I have my drain and my source, and the current flowing through my drain will equal to half Kn prime W over L VGS, blah, blah, blah. VGS minus VTN squared, right? We will show a better model of so this is called the large signal equivalent circuit. This is the large signal equivalent circuit. We will have a better drawing of it next with an actual current source drawn. They don't draw it here nicely. Okay, so in this, again, this is an example. Please go through it. I will not go through it. I will go through one that's more relevant, just because of the timing issue, right? But I will go. This one basically just goes through some of the various voltage levels. Put the source at a certain value. What is voltage overdrive? What is threshold? What is gate to source? What is gate to drain? So it's good practice on understanding all the material we discussed. So very straightforward substituting the equations for the drain current. So please go over that. I will go over another one later. Okay, finite output resistance. I talked about that. We talked about channel length modulation, right? We talked about the channel being pinched earlier, right? If the channel is pinched earlier than the drain, then this is what the channel will look like. What's happening here? Why did this happen? Because I kept increasing the drain to source the gate to drain voltage. Gate to drain voltage was proportional to the increase in the drain to source voltage, right? So there was some of this happening here. So when we altered the electric field here considerably, right, we sort of pinched the channel further. Right? That was in yesterday's discussion here. If we do that, current is still going to flow. Right, and what is really happening? What happens when VDS is equal to VOV? And the characteristics of the device, VDS. When VDS is equal to VOV, what happens? Saturation. I start entering saturation, right? So every time so I've entered saturation here. If I keep increasing VDS, am I leaving saturation? No, I'm still in saturation mode. So here, if I keep increasing VDS, I'm still in saturation mode, right? But we assume that the current will not change.
What does it mean for the MOSFET to be like? What characteristics does it show when it's in saturation?
This is exact. The current will look like, the current will be fixed regardless of how much extra VDS you will be supplying.
Okay.
That's exactly what will happen here. But that's ideally that's what's going to happen. What we realized yesterday from the physics is that I keep increasing VDS, then I'm increasing what? This electric field here as well, right? So VDS increase means that the voltage between the drain and the source is increasing, means that electric field is increasing. So higher electric fields will do what? Will find more charges to pull along. They will find more charges that were not even in the channel to pull along, right? So yeah, this is D, this is S. The voltage difference VDS is what I'm changing. So there will be since there's a voltage difference between the drain and the source that is increasing. That means the electric field between the drain and the source will be increasing, right? So if it increases, it will find charges. It will easily find charges to pull with the electric field and against it to create the current, right? The holes and electrons to create current flow, correct? So it will be able to add more current. What does that mean? That means that this is not fixed in practice. This will look like a slope. That's all this means. And it also means for the model, it means that my current source that I had at the output will no longer be a current source with an infinite impedance in parallel. It would have a fixed output impedance. That's all that means. No, but this is reality. No, we don't want it. Ideally, I would prefer to have it straight line. But what we see is that this R output is very big anyway. We will see that this R output is big. So the slope here is very small. Small. I magnified it here, but it's a small slope. And so, but this is happening in reality. We have no control over it. And again, it will be more prominent when? Anytime, remember these devices, we're trying to shrink more devices and shrink more devices in a package, right? So if I shrink more devices, that means the length of the channel will shrink. That means what? That means the effect of channel length modulation will be more prominent, right? If I'm gonna shrink the length, L is becoming smaller and smaller. Then, if it was a big channel and I reduced the channel length by a certain amount, when it was a big channel, I don't see it. It's not the effect is not significant. But if the channels become smaller and smaller and smaller because I want to cram more devices on a chip, right? Then this effect will become more prominent, yeah, right? So it's a problem, but that's why if you look at, if you go and review, for example, take a processor from Intel and look at the previous, all the families all the way back to 20 years, for example, data sheets, pick them up. You will find that the voltage levels that are utilized by processors have kept decreasing. Why? Well, if you allow bigger voltages, then you allow stuff like this to happen. Right? Because why is this happening? Because I'm applying a bigger drain source voltage.
So to control the problem, I apply.
You're playing with lower voltages. Yes, all your electronics now, back when I was playing with electronics, fine. 5 volts was always what you used as a supply voltage, and always what you were utilizing in your digital circuits. Now it's, most of the stuff is 1.8 or 3.3. Right? So it's because, fine, if you have big voltages, then you're exposed to this channel length modulation issue. Then you're exposed to, you're going away from the ideal nice model of the amplifier which we want. Ideal current source that's controlled by gate voltage, right? That's what we want. But you're going to go away from that, right? So, but at the same time, you want to produce more functions on a single chip. So you increase the number of chips, so the length becomes smaller. So what do you do to fix all of that? You keep decreasing the voltage that you can play with. Okay? So, off topic, but I think it's important, right? So what did this channel length modulation do? Add current. So there's a factor here called channel length modulation factor. And basically now I have this was my original current, right? I multiply by 1 plus lambda VDS. Lambda VDS, so it's now I have my original current plus a little bit more due to this channel length modulation.
This current will go to the case
No, it's in saturation mode. Yes, in saturation, it's this lambda is now due to the channel length modulation. As soon as I've reduced my channel length, it's because I did what? Because I increased my voltage. If I increase my voltage, I am going to be able to pull charges easily. So current will be increased a little bit. So that's what this is. Okay. And 1 over this factor lambda is called VA. It's called this early voltage. The guy that discovered this is called J.M. Early. So they called it after his name. Right? So when you discover something, they call it after your name. So make sure you discover something useful. Okay, so you don't want your name associated with something not useful. Yeah. Shab, yeah. Okay, so and VA, this VA is about 5 microvolt per micrometer to 50 volts per micrometer. That's it's sort of the term. So how is this VA calculated? Again, it's not very important for us, but I just want to show you. So the VA is the slope of this line in the saturation mode, which is highly exaggerated here. Okay, this is highly exaggerated. I mean, if you want to look at real slopes, pick up a data sheet for a MOSFET and look at the ID versus VDS characteristic. You will see that this is highly exaggerated. I will try to do that tomorrow. So I keep forgetting to bring a data sheet. But all data sheets will contain the ID versus VDS characteristics for the device. If you extend this sloped line here all the way to the horizontal axis, it will intersect the horizontal axis at a certain voltage, VA or minus VA in this case, and that's how you can calculate your lambda. Yes?
And is it the same one that we found in the lab? There was delta Y over delta X.
No, that's probably the slope here. I think that's what you did in the lab.
No, we did also in that. It was delta Y over delta X all over the ID. Is it the same
I'm
number?
not sure what you did in the lab, honestly. So we can look at it. I mean, bring the lab. I mean, we can look at it in my office after this.
Here it only says lambda. It doesn't say what number.
No, this is due to channel length modulation. I don't think you did that in the lab. I
But
think
I mean, like, what is the equation for
I think you were looking at the slope only. I think you were looking at the slope in the triode region. I think that's what you were looking at. Yeah. So, okay. So now this is now the model we're talking about. Okay. So this is the equation for current. Remember, this equation is only where? Where is this? Saturation. Because it does not depend on VDS, right? As soon as you don't see VDS, then it's saturation mode. How did we deal with this slope? We dealt with it by putting this R output. So instead of having an ideal current source, ID, we have a current source that is now going to lose some current through this resistor. Right? Okay, so we're okay with this? So this is the model. Anytime you see the MOSFET now, you can replace it with this model. If you did what? If you biased it to operate in the saturation region. How do you bias it to operate in the saturation region? How do you do that? Here. This stuff is here. You put the gate voltage at a certain level that is higher than VT, which gives you an overdrive. And then you do what? Then you make sure that you put your drain at a level higher than your overdrive voltage. No, you can make it anywhere. You can make it as long as it's higher than the overdrive voltage. Your drain to source has to be higher than the overdrive. How much higher than the overdrive? It doesn't matter, because look at the characteristic here. Put as much as you want. I don't care. Okay? So that's what we will have to do next. We will have to put the device in this condition. Right? After you put the devices in this condition, okay, now we're in this zone. Right? We're in the right zone. After you're in the right, after you're in the zone, then you can do what?
Then you can do it like,
Then you can do small signal analysis. Then you can put a small signal and then start amplifying. Right? Because we will, if we're here, if we're in this zone, if we're in this zone, if we're in this zone, you agree that we're in saturation. If we're in this zone, we're in the saturation region. Now, let's say I play with VGS and I put a small sine wave on top of VGS. Right? What is that going to do to my? This is VGS. Remember, this is at one value of VGS. This is another value of VGS, another value of VGS. Right? So what we're going to do next is, okay, now I'm in the saturation region. Okay. Now what do I need to do? I want to have a signal that I want to amplify. So I put my device in the saturation region, and then depending on where I am in the saturation region, I will be able to amplify the signal magnitude in a certain way. We will see how to do that.
All the signal will be amplified, or just
Okay, so there's a large signal analysis. This large signal analysis will be putting. So I understand what you're saying. So you need to we will need to put my gate and drain and source at certain levels, right? So it's these when you put the drain and source and gate at certain levels, you are on one of these characteristic curves. Then once you're on one of these characteristic curves, we will add another signal in series with this gate to source voltage, if you want to call it. Yeah, and that's the one that we will be amplifying even further. Right? We will look at that. We will look at an example with detail. But first, let's figure out how to. Okay, so this is again we finished the discussion on the. So this is the model we talked about, And again, the R output is calculated from the slope of this line, right? So it's the slope of the ID versus VDS. So it's the slope of the ID versus VDS. So it's 1 over the slope, sorry, because here it's I over V. So it's 1 over this slope is equal to R output. So we calculated R output, and lo and behold, it's equal to what? Our output happens to be 1 over lambda ID, where ID is what? ID is the drain current without considering the
And then there's one over
effect of lambda.
And then there's one over VA, so that's why it's I'm not equal to V over I on load.
Yeah, 1 over lambda is VA. So this VA is what what you can calculate experimentally, right? If you know that slope, and you have that slope experimentally, you know what your VA is, because that's the intersection of your slope with the horizontal axis. So you can calculate this R output. You can actually do this calculation, right? And ID will be the value of current that you are operating at. The specific value of current on the characteristics curve, right? So this is ID, right? At a specific value of ID, you want to be able to calculate that slope. So it just happens to be that, it makes sense that it's affected by the value of which curve you're on, right? It makes a lot of sense because it's the value of it is depending on the slope where it intersects with the horizontal axis. So if you're on a low gate voltage versus a high gate voltage, you have to know which characteristic curve you're on. 1 over the slope is R, because here's I, here's V. 1 over the slope is R. But if you're operating here, definitely, you need to know which ID you're operating on. So it depends on which of these curves you're operating on. It makes sense, yeah. That it's dependent on the ID. Okay, P channel. As we said, we will only skim through the P channel because it's exactly the same, except everything is negative. So the current is flowing from source to the drain, not drain to the source, right? We said that current will flow from the source to the drain. And all the voltages, so we had, in our NMOS we had, the current was, voltage was the source here, then the gate, then the drain was moving, depending on where you are, the drain was moving around, right? Here in the PMOS, the source is here, then the gate is a little lower, more negative, and the drain is moving around depending on if you're triode or saturation, right? So exactly the same, but current direction is changed, and the values are all flipped. The negative voltages are all flipped in polarity, and that's why the equation for ID is exactly the same as before, except that instead of using VT, we use the absolute value of VT, because VT here is going to be negative. And then same thing with the effect of lambda. Lambda would be negative slope, so we convert everything everything that can go negative, we put an absolute value around it. But the analysis is exactly the same. Exact same analysis, yeah. So that's what we see here. All the voltages that can go negative are just put an absolute value. And this is a summary of the PMOS device. Same triode region, then saturation region. The limit between the triode and saturation is where the drain to source voltage or source to drain voltage is greater than or equal to the absolute value of overdrive. Because again, overdrive here will be negative as well, right? Because everything will be negative. All the voltages that we're talking about will be negative. So, and then we have the same current equations in the triode region, current equation in the saturation region. So follow exactly the same model, exactly the same steps. Yeah. And this is what I'm talking about, right? So flipping everything. Initially we had source and then gate above it, drain. Here, source and then threshold and then gate and then drain. Depends on where you triode or saturation. Right? It's just negative. We will do an example now. Okay, I understand we need to do an example there. So MOSFETs at DC. So this is where. So all of this is nice introduction that we did before. Now is how do we really make this happen? How do you really make this happen is now we have to make sure that we put the gate, drain, and source at the right voltage levels. That's what we will do first. That's called the DC point analysis or bias point analysis, or DC point or bias point analysis. So now let's look at this example. So we have a circuit, and again, just to note, in the NMOS, this is my source, this is my gate, and my drain, can be anywhere, right? So this does not need to be at 0, right? As long as you keep the source the lowest potential, the gate higher potential than VT, and drain, depending on triode or saturation, moving around, right? This is VT. So that's why if you look at here, they give you an example where, okay, you have the gate at 0. Right? Is that okay or not okay? It's okay. I mean, I put the gate at 0 volts, that's fine. So I have, now I know my gate here is at 0 volts. What do you need to do? So what are they asking? They're asking, design the circuit of figure 5.4 in figure 5.21. Where is that? Which page am I on? Huh? What? Yeah, this is figure 5.2. Okay. So design the circuit figure 5.21. That is, determine the values of RD. They want you to determine the values of RD and RS so that we do what? So that transistor operates at ID equals 0.4 milliamps. So we want ID to be equal to 0.4 milliamps. The objective is 0.4 milliamps ID. This is my ID. Remember, we have our equations for ID. And VD is 0.5 volts. The NMOS has VT of so and so, mu naught, mu n times COX, so and so. These are the device parameters, right? WM, blah, 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 right? And then they said, okay, forget about channel length modulation, right? So lambda is 0, meaning what? Meaning my characteristic curves look like this, straight line here. Okay, so that's typically what we're going to do, by the way. Okay. So what are we going to do here? So they're telling us that I have a supply voltage of 2.5 volts here. And then I have a supply voltage here of minus 2.5 volts. Right? So I still don't know what this is my drain voltage. Where's my source voltage here? This is my source voltage, right? So what do I need to do? I want to operate. My objective, by the way, is to operate in to build an amplifier, right? That's my objective, is to build an amplifier. They should have said that here, but the objective is to build an amplifier. So let's see if what they're saying will help us build an amplifier, right? So they're telling us that the gate voltage is at 0.5. They're telling us that the threshold voltage is 0.7. So threshold voltage is 0. Let me erase this. The drain is 0.5, yes. The gate is at 0. And then I have a source somewhere. This is my source. And I don't know where it is yet. So this is 0 volts, right? And I have my source somewhere. And because it's unknown, because I don't know the current in the drain. Or they did tell us they want the drain current to be 0.4 milliamps. So but I don't know RS. If I know RS, then I can find the source voltage, right? I don't know the source voltage yet. So this is somewhere, right? And I want to make sure that, so this somewhere, 0.7 above this somewhere is my VT, right? This is 0.7 volts. This is VS plus 0.7 volts, right? That's my threshold voltage. So VD is 0.5 volts. So VD is definitely above the gate voltage. This is VD with respect to the gate voltage, because this is VD with respect to ground, is at 0.5 volts. This is VD. Right, so my source is somewhere. I need to find that out, and then the drain voltage is here and gate voltage is here. This is 0.5 volts, 0.5 volts. The difference between my gate to drain voltage, if you look at our summary, if you look at our summary for the NMOS device, let's look at the summary for the NMOS device. Where is that summary? Here. So in saturation, the gate to drain voltage has to be less than or equal to the threshold voltage, and the drain to source voltage has to be greater than the overdrive voltage. So that's something that we know from the summary. So do we have the gate voltage? Yes. Do we have so we have our gate voltage and we have our threshold voltage that they were given, and we have the W over L, so we should be able to calculate ID, I believe. What?
We don't need the voltage.
No, we need the voltage, source voltage. Yeah, we want to check that we are operating in the right zone. Yeah. So what? First, let's do a few things. So we know that this is 2.5 volts. The voltage here is 2.5. How about the voltage at the drain? It's 0.5, right? So we know the voltage at here, and we know the voltage here. And we know, so the difference between these voltages divided by the resistance is the current. And we were given the current, right? So I can calculate the resistance by the difference in voltage divided by the current. So that's 5 kilo ohms. Okay, to determine the value required for RS, we need to know the voltage at the source, right? We still don't know the voltage at the source, which can be easily found if we know the gate to source voltage. So how can we find the gate to source voltage, right? Still we don't know. This in turn can be determined from the overdrive. Toward that end, we note that since the drain voltage is 0.5, greater than VG, the NMOS is operating in saturation region. So this is 0.5 volts above the gate. Remember, when we were in triode, when we were in triode, we were what? Where was the drain voltage? Drain voltage was small. When it became greater than the overdrive voltage, overdrive is what? It's the gate minus the threshold. So this is my overdrive voltage, right? So this is my overdrive voltage, and this is my threshold voltage, and this is my overdrive voltage again. This is the minimum overdrive voltage that I can live with to go into saturation. Now I know from here that my drain is above my gate voltage. If the drain is above my gate voltage, and this gate voltage is equal to the threshold voltage plus an overdrive. So the gate voltage is equal to the threshold voltage plus an overdrive. And my drain is above that. That means my gate voltage is definitely, my drain voltage is definitely way above the overdrive voltage of the device. Right? So since that's the case, it means what? That my drain to source is greater than the overdrive. Overdrive is this, right? We know that my source is somewhere below, right? And because it's fine, it's connected to there's a negative voltage here. It's a little bit, it's negative, but how much more negative, I don't know, right? That's what we need to find out. The gate is at 0, and we are operating with an overdrive above VT. So drain is half a volt even beyond the gate voltage. So that it means that the drain to source voltage is significantly over the overdrive voltage, right? So we're operating in saturation mode. So which means I can use this equation for current. That's the whole objective. I can use this equation for current, right? The equation for current is the one that does not depend on VDS. Yes? No? So if this is my equation for current, I'm given the current is 0.4 milliamps. So they rewrite it in convenient units so that they can easily have things cancel out. What I need to know is my overdrive voltage. So that I will be able to calculate, because if I know this, I know everything, but I do not, and I know my gate voltage, I know my threshold voltage, but I don't know my source voltage level, right? So I need to, for me to be, the V overdrive is what? The gate to source voltage, which I don't know, minus VT, right? So I'm trying to calculate the overdrive so that I can calculate my gate to source voltage, right? So if I substitute in this equation, I'll be able to calculate my overdrive voltage. From my overdrive voltage, which is equal to the gate to source voltage minus the threshold voltage, I can now place my level of my source voltage. So it's at minus 1.2 volts. You got your overdrive. Your overdrive is from this equation.
So we don't need to
No, the levels I was drawing was just for you to understand what was missing here. So we had
from the drawing, I can check and then I don't have to get the V source. And do I need the value of the V source?
yes, because if you don't have the value of the V source, how can you just select the value of the RS? Remember, we don't have RS and we don't have RD. That's the objective, is to design this. How are we gonna, the whole objective behind putting the device in DC operating point, the way we will do that is by fixing VD and VS to a certain value. How do you fix VD and VS to a certain value? It's by, exactly, how do you control the voltage here? By putting a resistor. You want to operate, remember, you want to operate at a certain DC operating characteristic, meaning a certain value of ID. You want to operate at a certain value of ID. So you're given ID of 0.4 milliamps. So you are here. You know that you are here. Where? Where here will define VDS, right? You need to find out where here. Right? Where are you here?
Does it matter where exactly? Because we're on like saturation.
No, it will matter. It will matter for small signal analysis. Okay. For now, it does not matter. Okay, but it will matter for small signal analysis. Right? So you are here, but you don't know where. You want to find out where. So you need to find VDS. So VD we found. No problem. This is the current flowing here. You know it. The voltage difference divided by the resistance. Now, we do not know VS. How do you find VS? This is minus 2.5 volts. Right? We do not know VDS. For you to find VS, for example, one good way to find VGS. If I find VGS, I know that what? The overdrive voltage, so VGS minus VT is equal to my overdrive voltage. Then from there I can do what? If I find VGS,
Do we have
so I can, do you agree that we can find the overdrive voltage from here? From the ID?
So we don't have VGS.
No, but I don't care. I have an overdrive voltage. I can find the overdrive voltage because I know ID, right? And the value of ID is not dependent on VDS. Not dependent on VDS in saturation mode, right? So ID is equal to device characteristics times overdrive voltage. That's what ID is equal to, correct? So if that's the case, I know ID. These are all the device characteristic, capacitance, length, width that they gave me. I can find the overdrive voltage. If I find the overdrive voltage, it is equal to the VGS minus VT. I have VT and I have the overdrive voltage, which means I can find the gate to source voltage. If I find the gate to source voltage, then I know what my voltage of my source is with respect to the gate. Gate is at 0 volts. We found VGS to be 1.2 volts, which means my source is at negative 1.2. So here is at negative 1.2 volts. So this is negative 1.2, this is negative 2.5. The difference between them divided by this resistor is equal to 0.4 milliamps because that's the same drain current flowing through. Okay? And that's it really. And that is your DC operating point analysis. So this is your DC operating point. So now we've put the device, so this is one example. Okay, there are tons of examples. I cannot solve all of them. I think please go through. They all use the same current equation that we discussed. But some of them are more complicated than the others, right? So, but they are good examples. But again, look at the equations. There is nothing different than the equation that we've been discussing here. So, that being the case, so all of these are examples. So please go through them. But they're all doing what? They're all putting my device at a certain DC operating point, certain ID, and a certain VDS corresponding to that, right? After we do that, we will want to figure out how to operate the device as an amplifier. How do you operate the device as an amplifier? I'll just start here and then we'll stop very quickly. So remember, we were producing what? We were producing a characteristic that looked like this. This was ID for various values of VDS, and we wanted to operate in saturation mode. We made sure that VDS is greater than overdrive voltage, right? To operate in saturation mode. If we do that, we get a fixed current, correct? At the output of my model. My model looked like a current source controlled by a certain overdrive voltage. That's what my model looked like.
And what we did was define current.
Yes, I created a voltage controlled current source. Right? I created a voltage controlled current source. So now, if I have a voltage controlled current source, this is my voltage controlled current source. It's controlled by what voltage? Controlled by VGS voltage, or the overdrive voltage, right? It's controlled by VGS. So this is my voltage controlled current source. Then we added some resistance here, our output to deal with stuff, but we will typically not use that. This is what? My drain. This is what? My source. If I would like to now get an output voltage, typically that's what we want, right? In op amps, what were we doing? Putting a voltage, getting another voltage at the output, amplifying the voltages that we wanted, right? If I want to amplify a voltage, one way to do that is to put a resistor here. If I put a resistor here and I connect this to ground, which is the example we just did, right? I have some voltage VDD here. I put some resistor RD here, and this is my source connected to ground, for example, and I measure here. This will be my output. I will take my output here. This is VDS. If I take my output here, am I controlling the value of output using ID or not? If I increase the current here, what's the current here is ID. Do you agree? This is ID current. And this is from the equations that we derived for the various regions. But we are only concerned now about saturation mode, because this model is only valid in saturation.
Current is the same.
The current is the same, so the current is ID. This current is ID. I will have a voltage output VDS here equal to what? Is VDD
The difference between
minus ID times RD. That is my voltage output. Right? So I will have a voltage output here.
It's like a zero.
This is Kirchhoff voltage law. So VZ0 minus IDR. That's fine. That's fine. I'll give you credit for that you're studying for tomorrow's exam. That's fine. Today's exam. That's fine. So anyway, this is my output voltage. This output voltage is controlled by the value of ID. This value of ID I'm controlling by gate, which is a nice thing. I could have taken the output here, by the way. Some people, you may tell me, okay, why don't you just take the output here? Taking the output here is a problem because this is not reference to ground. Right? This is a float. Remember that differential signal we talked about in op amps? This is the differential signal. It is not correct with respect to ground. So typically, what? You don't need, VS is here. I connect the VS to ground, right? But now I want to amplify my signal. Right? I have a signal VGS that I would like to amplify. Right? I know that I can produce a current ID controlled by VGS, right? That's from the equation we got before, and that is this value of ID, okay? This value of ID, I know I can control it using VGS, but I now need to create an output voltage. I want to amplify an output signal placed here. How do I get an output voltage signal amplified that I've placed at my input? One way to do it is place a resistor, right? And I can do two things. I can either take my output voltage across this resistor, and it's fine. The output voltage across this is ID times RD. So, and I have basically a voltage, ID times RD. This is a voltage that is controlled by ID, which is controlled by VGS, which satisfies my objective. But this is a resistor that is not referenced to ground. So if you are measuring something, you're measuring a voltage level. You want to measure a voltage level with respect to ground. Typically, your battery, your portable devices, everything has a reference. So typically we use a reference of 0 volts. Right? That's our typical reference in electric circuits. Right? So that's why it makes a lot of sense to take your output across here, across VDS. And VDS is VDD minus ID times RD. So I still get an output that is controlled by ID, which is controlled by my gate voltage. Do we agree? So that is where we start taking our op amp output for amplifier operation. We will stop here Tomorrow we'll do the small signal. So today we did DC operating point. We put it somewhere on the curves. Now this somewhere we will zoom in and then see, okay, if I put a small signal, how will it be amplified? So we'll do that tomorrow, inshallah, and that's the end of the chapter. That's